The same proximal policy optimization that RL agents use, ported word for word onto a wave function, trains a 1.5 billion parameter neural network as a quantum state, 3 orders of magnitude beyond what? What if the math that trains a chatbot also finds the ground state of a quantum magnet? Anyone had done before, no physics rewrite, just the RL playbook, the setup. A quantum, many-body system of n spins lives in a 2 to the n dimensional space. A neural quantum state parameterizes the wave function, and by the Born rule, the squared amplitude is a probability over spin configurations. Finding the ground state becomes variational energy minimization. The dominant optimizer, stochastic reconfiguration, preconditions. The gradient with the Fubini study metric, which means solving a large, often ill-conditioned linear system every step, the cost that blocks scale. The authors notice a correspondence. Spin configurations are actions. Centered local energies are advantages. The Born distribution is the policy. Variational energy minimization, IS, and advantage policy gradient update. So they port PPO directly onto the wave function. They call it proximal wave function optimization. Sample a batch of spin configurations from the current wave function, cache the real and imaginary advantages, then for k inner epochs reuse that batch. The amplitude channel clips the probability ratio exactly like PPO. The genuinely novel piece is the phase channel. Frustrated Hamiltonians need complex valued wave functions, so they clip the wrapped phase increment and weight it with detached importance weights to correct the stale reference. A first-order consistency theorem proves the very first inner update equals the true variational gradient, and an infidelity bound plays the role of the trust region that licenses sample reuse. First cost picture. Per iteration, proximal wave function optimization runs in 0.022 seconds, about 12 times faster than Spring, 5 times faster than Atom, and 14 times faster than min-SR, despite the extra. Because the proximal objective reuses one batch across 4 inner epochs, it amortizes the dominant cost, sampling, and local energy evaluation that Atom repays every update. Bookkeeping for ratios, clipping, and wrapped phase. On the sign problem, free transverse field Ising chain, both reach a relative error of 1 in 10 million, but the proximal update gets there in about 5 minutes while min-SR needs 30. The real test is the frustrated Heisenberg J1-J2 chain, where the phase channel is active. There, the proximal update hits 1 in 10 million in 15 minutes with a steadily decreasing energy variance. Min-SR plus Spring gets stuck 3 orders of magnitude higher, and plain min-SR diverges to nan on most seeds. Here's the picture. A frustrated magnet has spins locked in a rigid grid of competing alignments, a stiff, conflict-laden configuration space. The wave function that finds its ground state behaves like a fluid probability wave, flowing and reshaping across that grid until it settles into the lowest energy mode. The proximal update is what lets that wave flow without diverging. Stability is the headline the metrics miss. Across 10 seeds on the frustrated chain, the proximal update is stable on all 10. Min-SR diverges to nan on 6 of them. Reporting only the interquartile mean hides this because unstable runs produce extreme outliers that drag the average. A faster mean is not the same as a method that survives every random seed. 3 honest caveats. First, the improvement certificate holds under a stronger global clip condition than the per-batch algorithm actually enforces, so it is a certificate of direction, not a guarantee on every step. Second, part of the wall clock win comes from doing more optimization steps per unit time. Because sample reuse amortizes the local energy cost, Atom eventually reaches lower energies given a full 4 hours. Third, the 1.5 billion parameter RWKV7 result is a scaling demonstration, not a claim that language models are the right tool for one-dimensional spin chains. Proximal wave function optimization. The same clipped surrogate that stabilizes robot learning also stabilizes a quantum wave function. Variational energy minimization recast as policy gradient, scaling neural quantum states past a billion parameters. Subscribe for the next breakdown.